いいですかね。はい。演題はですね、実運用に耐えるエージェント AI ループの設計、ロボティクスを視野に入れた実システム信頼性を担保する、実践的 AI フレームワークと題してですね、チラーグ・アグラワースさん、この方はですね、アレクサプラスの AI エージェントエンジニアリング部シニアソフトウェアエンジニアでいらっしゃいます。Amazon.com の方です。Next topic is designing agentic loops that actually ship practical frameworks for building reliable AI agents in robotics and production systems by Mr. Chirag Agnawal, senior software engineer from Amazon.com. So please start the presentation.
All right. Hello, everyone.
So please.
Am I audible?
Okay.
And can you see my
yes,
screen?
Yes.
Okay. Okay. Well, hi, everyone. I'm Chirag Agrawal. I'm a senior software engineer at Amazon. It's a pleasure to meet all of you today. I'm going to talk about building AI agents for production use cases. We'll cover core concepts of agent design and implementation and see how they fit together into a practical framework. I hope you're having a great time at the RISC-V day in Tokyo. I'm excited to dive in. So first, a little bit about me. I'm one of the lead engineers behind Alexa's Brain, the part that makes Alexa useful and intelligent assistant. My job is primarily to make Alexa do three things at a massive scale. First one being to pick the right action to help you with your request. Second one is to remember what you just said to keep the conversation natural and smooth. And the third one is to do everything extremely fast. I work on the conversational AI platform that internal teams and external partners can plug into. So instead of building everything from scratch, they just add new capability into Alexa's Brain. So this is our roadmap for today. We'll start with in-context learning, and then each topic will build on the previous one. By the end, we will have a practical framework for building agents that can run reliably. So first, I want to start with a very simple example, and this will give you an idea of how AI learns in real time. So on the screen, we have a prompt. You can copy paste this into any AI chat interface if you want to replicate this exercise. The prompt starts with the word cat on the left. It is followed by an arrow and then the word tack. On the second line, we have another word rice and then an arrow and then the letters ECIR. And then on the third line, we have the word smart, followed by an arrow and then nothing. So if you put this prompt if you give it to an LLM, we'll get a completion that says cramps. If you look at the words on the right, they are basically the words on the left, but reversed. And the interesting part here is that the model was never told to like reverse these words. All we did was give it a couple of examples, and then we gave it a new word. The model recognized the pattern from the examples and applied it to new data without any training. So this property is called in-context learning. It's basically LLM's ability to learn from examples in the prompt and generalize it to new inputs. And this ability is at the very heart of AI agents. So before the advent of GPT, achieving something like this required substantial resources and expertise. Uh, but with modern GPTs, this is not the case. These are basically massive neural networks that are trained on internet scale data, and they exhibit emergent properties like in context learning. So these models learn without any training. All we need to do is give them a few examples, sometimes not even that, and they can still accomplish the goal. What this means practically is that these neural networks can be programmed in real time, and that has huge implications for the technology industry. So, this brings us to an interesting analogy for today's session, and that is LLMs should be seen as new kind of computer. Uh, LLM comes with a lot of knowledge prepackaged and compressed in the form of its model weights. We program it by writing instructions in natural language. That is the prompt for the model. And we can load external state into it through context window, just like putting data into the RAM. So once you think of it this way, you can argue that if we build scaffolding around the LLM, we can harness its intelligence like a CPU to make decisions, to execute workflows, and manipulate external data. That's the foundation we'll use to design our agents. So I want to cover how an AI agent interacts with external world. And to make this example, to make this idea concrete, I'll take a simple example of planning a picnic. So let's say that we have an AI agent and the user wants the agent's help to plan a picnic. Uh, the user might say something like, I want to plan a picnic for tomorrow in Central Park. Can you help me? From this one sentence, the agent can extract two critical inputs. One is the location of the picnic, another one is the date of the picnic. It might also ask follow up questions to the user about the time, food preferences, and activities they are interested in. So those are all direct user inputs. But there is a crucial piece of information that the user didn't give the agent, and the agent shouldn't keep asking the user every time, and that is the weather information for that date and place. So a good AI agent should realize that it cannot plan a picnic without checking the weather for that time and place. So when the AI agent reasons, ideally it should decide to fetch the weather from some external source. Um, so before we move further into this example and see how the agent would do that, I want to cover uh, what is the agent uh, means, like what goes in the prompt of an AI agent typically. Um, Here you can see that we have this blue box on the screen that represents the prompt, and it has multiple components. The first one is the system instructions on the top, and this includes instructions to use tools or to generate response. Uh, then uh, in the next section, we have a collection of tools. Uh, we'll cover more about this later. What does a tool mean, and how does an agent uses it? Uh, the third section has context, and the context could be any important domain specific detail. For example, current time and the history of the conversation between the human and the agent are common examples, but there could be other domain specific data in there. And the last one is the current request. So if we map that to our example for planning a picnic, the prompt would look something like this. It would have system instructions on the top for the agent. Then it will have a a collection of tools. Here we have three tools: a tool to get weather, a tool to convert units, and a tool to get latitude and longitude based on the place. Then we have contextual information, and then the user request. So, what is a tool? What does it mean? The agent obviously cannot magically get the weather information to plan the picnic. This is why we have to give it access to some tools. So, a tool is essentially a function that an agent can call. And it looks something like this, what you see on the screen. A tool has a name, it has parameters, it has response shape, and then it has description of what the tool does. And the description is in natural language so that the LLM can reason with it. So if we play out the example for planning a picnic, uh, this is how it would look. The agent reasons over the user request and the tool in its prompts, and it decides that to plan a picnic, I need to call the get weather tool because I need the weather information. And it produces this tool call that you see on the screen. So this two-step process is called the React framework. Basically, it the LLM reasons over the context and takes action. So the React stands for reason plus act. When the model produces a tool call request, the framework around the model will intercept this tool call and it will turn that into a real API invocation request. So when the API is invoked, we will get an API response. And in this case, since we invoked the get weather tool, we will get the weather forecast in response. So this API response is added back to the agent's context alongside with the original request. So the agent has more information now than it started with. Uh, it has the user input, and now it has acquired this external state, which is the weather forecast. So in the React framework, typically there will be another inference with all this new information. And this time, the agent will decide that it doesn't need to invoke more tools. So it can go ahead and generate a concrete plan for the user. And what the plan is really depends on the weather. So if the forecast of the weather is good, then the agent might produce an itinerary. And if it's bad, then the agent might suggest to pick a different day for the picnic. So that's kind of like what makes this framework intelligent and powerful. If we zoom out of this example and see what's really happening here, we can see that the agent is continuously running in a loop in three stages. First one is perceive, second one is reason, and the third one is act. It only exits this loop when a terminating condition is satisfied. Typically, that is when the agent produces response for the human in the loop. So let's map it to the example we just saw. Uh, the agent perceives the current situation by reading everything in its context. And in this example, we had a bunch of tools, and the user request was the new information that was perceived by the agent. So given that user request, the model reasons what needs to happen next. So here it inferred that the user wants to plan a picnic, but the agent is missing critical piece of data, which is the weather. So during the reasoning step, the agent effectively thinks, to answer this well, I need weather information for that date and place. And since I have access to get weather tool, I'm going to invoke it. So in the next step, the agent decides to act on its decision to use the get weather tool. So the surrounding framework executes the tool call. It gets the real forecast and feeds that result back into the context. So now that we have acquired new information, that is that information would also be perceived by the agent, just like it perceived the user request. So this loop is started all over again, but with this time with more information, which is the weather forecast, and the agent would reason over this context data again, and this time it will say that I have all the information I need. I can create a itinerary for the picnic, and this time instead of deciding to call a tool, the agent would generate a natural language response for the user. So, uh, so this is what an agentic loop looks like. Uh, Perceiving the user input along with the current context, reasoning over all that information to decide what to do next, and then acting in the form of either tool calls or response to the human. If the action is a tool call, then the new data comes back into the context and the loop repeats. If the action is a final answer, then the loop terminates and the interaction is concluded. So this perceive, reason, act loop combined with in-context learning and access to external tools and external state, that's what turns a simple language model into an agent that can operate in real world in a reliable way. So now that we have seen how an agent works, the next important topic that I want to dive into is multi-agent systems. Uh, Multi-agent, in simplest words, it means multiple agents collaborating together to achieve a goal. There are many different orchestration patterns for multi-agent systems, but the most canonical one is where agents are arranged in a hierarchy where the top agent is the user agent. And the core idea of multi-agent system is that agent can use other agents just like they use tools, like we saw in the example earlier. The the agentic loop that we saw earlier is still the foundation of multi-agent system, but the difference is that now agents are composed not just with tools, but also with other agents that they can call. So let's look at a concrete example to understand that better. Here we have an assistant agent, and this agent directly talks to the user, and user can talk to it. And this agent has access to two other sub agents. One is the weather agent that we saw earlier. Um, this weather agent can tell us the weather forecast. And the second one is the device agent. So the device agent can control the devices in our home. Each of these agents in turn have access to their own set of tools. So if the user asks, as an example, turn on my sprinklers tomorrow morning if it doesn't rain today, the assistant agent will enter its agentic loop, starting with perceive. It will reason that it needs to first check with the weather agent whether it's going to rain tomorrow or not, or it would rain later today or not. So it will invoke the weather agent by producing this tool call that you see here. And in the argument, it will send a natural language message. So when this happens, the weather agent will start its own agentic loop. And this is same as what we saw earlier. So kind of like paints a picture of how multi-agent builds on the foundation of a single agentic loop. So weather agent will run its agentic loop, it will acquire weather information, and then it will produce a natural language response for the assistant agent. So this response is added to the context of assistant agent, and that agent will do another round of the agentic loop. This time it will reason that now that I know that the chances of precipitation are zero, I need to invoke the device agent and schedule the sprinkler to run. And when that happens, the device agent will run its own agentic loop and it will confirm that it has scheduled the sprinkler to run tomorrow. Um, this information is again given to the assistant agent, and it will run a third round of inference. And this time it would reason that now that I have uh, contacted the weather agent and then based on that scheduled the sprinkler to run, my job is done. So it will go ahead and produce a response for the human, and this interaction will conclude. So this is essentially a multi-agent workflow. And although this example was relatively simple, multi-agent systems promise a powerful paradigm where hundreds or even thousands of agents can collaborate to complete a task, which is far more complex than turning on a sprinkler. So there are industry protocols like A2A, which is proposed by Google, and MCP, which is proposed by Anthropic, which are taking us exactly towards this future. If you're building robots, all of this thinking about agentic loop, React, and multi-agent systems still applies. The agentic loop is basically the skeleton of autonomy. Uh, the robot would have access to a different set of tools, such as the ones for physical movement, and it would receive multimodal input such as camera feed or obstacle map or microphone audio. But essentially, it reasons over this sensory input and the available tools, like it did in the example we just saw. And it acts in the real world and then immediately go back to perceive step to see what actually happened. Uh, the important point is that autonomy comes from running this loop continuously with the right set of tools and context. Once you see the robot this way, um, we can argue that uh, a robot is an embodied AI agent with motors and sensors attached, and all the ideas about tool orchestration and multi-agent collaboration carry straight over into the physical world of the robot. Um, okay, so moving on to the next topic on our agenda. Uh, so far, we have been living in mostly in the logical world. We talked about the agent as loop and tools, and we talked about multi-agent systems. Uh, excuse me. The other important dimension to this topic is where does the inference happens? Uh, One of the obvious answers is that it can happen in the cloud. That's where most of the AI agents are running, but it can also happen locally on the robot's own hardware. Um, so in the next few slides, I want to zoom in on local inference. Uh, we'll cover how running parts of agentic loop on the robot itself changes things like latency, reliability, privacy, and why things like RISC-V matter for scalable autonomy. So in the first part of the talk, I framed LLM as the new kind of computer. Uh, Weights behave like CPU, context window behave like the RAM, and prompt is the program. Uh, for a robot, that mental model is even more concrete uh, because we are literally deciding where to mount this new computer. Uh, and as I said earlier, it can live in a server rack, but it can also live inside robot's own compute stack. So let's go over some pros and cons here. Um, if we keep the LLM entirely in the cloud, we can afford a larger model, which runs on shared GPUs with lots of memory. So this is great for very difficult planning tasks or long horizon reasoning, but it comes with higher cost per token and it has fixed network latency. And obviously, there are privacy and reliability concerns. If we push a smaller model onto the robot itself, uh, we have to work with a tight power and memory budget. But the upside is that we gain lower latency, We are not exposed to network outages or privacy risks, and we keep a lot of the raw sensor data and user data on the device, which is the robot. So when I say local inference, I want to make it concrete with some example. We can imagine that on the RISC-V device, the robot has its own tiny memory and a tool set. It is not just pushing everything into the cloud. It is doing device semantic retrieval over a small vector index. So this is essentially acting as robot's short-term memory, and it stays private on the device, never leaves, and goes to the cloud. Uh, on top of that, we wrap sensors and peripherals as local LLM tools. So instead of calling a remote API like we saw in the weather example, the agentic loop will call something like get the camera frame or get microphone buffer or like check the device state. Uh, the agent is not directly talking to the hardware. It is talking to these tool abstractions, just like uh, it would talk to any other API. So like this agentic loop that we saw earlier provides a nice abstraction over like hardware components of the robot. And because all of this lives on the device, the robot can keep working even when the network is gone. It can perceive, still see last few observations between the user, the robot, and the external environment, and keep it in the local index. And it can still run a simple reasoning steps entirely on the device using a small language model. Um, so once we have a local tool set on the device, the next question is when does the robot handle a request locally, and when does it delegate it to a bigger model which is running on the cloud? uh, and this decision itself could be made by a lightweight ML classifier that also runs locally on the device. So the the pattern here is that every request comes into the agent and goes through that classifier first. The classifier looks at the request, and if it's a simple request that fits the local capabilities, uh, then we can execute it entirely on the device using the local tools and the local memory, using the local models. But if the request is complex or requires access to lots of external knowledge or long horizon reasoning, then the classifier will route it to a model which is hosted in the cloud. Uh, One of the advantages of doing it like this, using an ML classifier, is that it can also account for policies like latency requirements, privacy, the current battery status, and the capabilities of the local tools to make this decision. Uh, a simple example is that a mobile robot on a small battery will have different threshold for what can be executed locally compared to a robot that is plugged in and it's running on a factory floor. Another interesting angle for local models is the context management. Uh, Before anything leaves the robot, a small language model on the device can compress and summarize the conversation or the interactions that the robot had so far with the user and its external environment. Uh, it can also redact sensitive or private information such as raw images from the home or any detailed operator identifiers, and only send a minimal compressed summary of the context to the model in the cloud. So the cloud model sees what it needs to respond correctly, but most uh, of the private details they stay on the robot. And the net effect is that the robot is constantly making two smart choices at the edge. First, it is deciding whether it even needs the cloud for a request or it can handle it locally. Second is if it does need the cloud, what is the smallest, safest kind of uh, slice of context it can send. So that combination is where the agentic loops, the RISC-V hardware, and the the autonomy of the robot really starts to line up. I also want to touch upon the open nature of RISC-V because it is part of the reason why local inference is getting more interesting. Uh, for robotics and local AI, the open instruction set that RISC-V provides matters a lot. An open ISA makes it much easier for different vendors, different countries to build their own uh, AI capable processors that can run small or at least a quantized language model. It also makes experimentation a lot easier. You can design a RISC-V based core with good vector support and low precision math that are tuned for things like vision mapping or small LLM inference. Uh, and over time, that means that we start seeing cheap AI friendly controllers in devices like routers or home robots or factory equipments. And from product teams perspective, that means that there are more places where we can realistically run the agentic loop on local AI instead of always relying on a larger model running in the cloud. Um, Lastly, I want to touch upon a huge advantage of local inference, and that is data privacy. If our robot can do perception and some amount of reasoning on the device, uh, fewer raw data needs to be shared with the external environment. And this is important if the robot is working, for example, in a home or in a hospital or in a factory. Uh, Local inference also improves control and auditability. Uh, so when more of the scenarios are handled locally, we can enforce logging and policy at the device boundary. If the underlying compute stack is built on open architecture like RISC-V, it becomes easier for regulators and customers to inspect and certify what's really happening on that device. And we don't need to trust a completely closed black box. And finally, it feeds back into agents' own behavior. If local models are first class tools, the request classifier can be biased to prefer them whenever a task involves sensitive data. And only when the task needs access to larger model or external system, the robot will decide to send the request outside of the device. Uh, to make that a bit more concrete for robotics, I want to show two simple patterns we can keep in mind. In the first pattern, the perception is local, reasoning is mixed between local model and cloud-based model, and the actions are all completely local. So you can think of a domestic robot that listens for commands and understands simple instructions and controls appliances. So the audio is processed on the robot. The planning is done locally for most of the task, and occasionally it relies on the cloud. And all the actions happen locally. So if the network is gone, the robot is still responsive and it respects, the local privacy expectations. The second pattern is where perception is local, but the reasoning is entirely in the cloud, and actions can be local or remote. So imagine a logistics robot that needs to coordinate with many external systems. It can handle raw sensor data locally, uh, And for heavy planning, it can redact that data and call a large language model. What RISC-V and local hardware gives us is the ability to use the first pattern in more places compared to where we are now. More robots can afford to keep perception and basic reasoning on the device and use the cloud only when the task truly demands it. Okay, so that's the end of this session. I I want you to like walk away with these six takeaways from this talk. LLM should be seen as a new type of computer. Prompts are essentially programs for that computer. In context learning is how a model generalizes a task over new data. Uh, React is the framework which is used by agents to reason and plan over tools. And agentic loop is what really powers a end-to-end product. Lastly, open hardware and local intelligence is what will truly democratize AI. Uh, so I hope that was helpful. And if there are any questions, I'll be happy to answer.
Thank you very much. Does anyone any questions? So I have one question. I understand that the agent system consists of many sub-agents and/or tools, and the combination of those agents and tools. So I want to know for coordinator point of view, how to know which tool is most useful for user question. I think it's something like robust filter function or something like that. That is important for the AI, small language model. So please teach us those questions.
Of course, great question. So just to summarize what you asked, essentially, an agent has access to different sub-agents and tools, but how does it know which are the right ones for the user request? This is a challenging problem, and there is a whole spectrum of solutions that are being developed to address it. The simplest thing we can do is we can add examples to the prompt for common scenarios, and that basically teaches the model that for requests like turning on lifting a cup or turning on a sprinkler, you need to use X, Y, and Z tools. So that's the simplest thing we can do. The more extreme end of this spectrum is to train your own language model, or essentially fine-tune an existing language model over lots of training data that is comprised of real-world scenarios that use the tools that your agent has access to. That dramatically improves the accuracy and also latency of the agent when it is operating in real scenarios. Between that, there are a lot of offline evaluation frameworks that have been developed. Essentially, what they do is you can generate or author a lot of test cases or sample these cases from production data, and then continuously measure the invocation accuracy of tools or subagents for your main agent. And this gives you concrete metrics that you can optimize by changing the prompt or modifying the tool definition or subagent definition. Does that answer your question?
Okay, thank you very much. I understand. So, is there any other have a question? なければ時間も参りましたので、はい。以上で、このセッションを終わりにしたいと思います。Thank you very much. Thank you very much.
Thank you.